Okay, in this problem we are looking at a dynamic equilibrium situation. So that's different from static equilibrium because it means that although we have no accelerations and the sum of our torques and forces are going to equal zero, we still have a velocity, a non-zero velocity. Okay, and it doesn't matter how big the velocity is, just as long as it's constant and non-zero, it would be considered dynamic equilibrium. Okay, so let's just write our equations that we're going to use here. We're going to have F net in x equals 0. We're going to have F net in y equals 0. And we're going to have our sum of torques, our net torque, equal 0. All right. And then we'll have to choose our pivot point. Okay. So if we look over here at our steps, we're going to draw our free body diagram, which is already done for us in the picture. All right. We're going to choose our pivot, the pivot point about which we're going to calculate all of our torques. We're then going to calculate, or I'll say just write, because it's really just a matter of just looking at the picture, write F net x, F net y, and torque net. All right. And then we're going to solve for unknowns. All right, so let's look at the problem and see what those unknowns are. Okay, and then, oh yeah, here I'll just write for dynamic equilibrium, V is a constant. Okay. All right, looks good. A person wants to push a lamp of mass, which we know is 7.2 kilograms. We're told the radius of the base and the height of the center of mass. And we're pushing this object or this lamp across the floor. The floor has a coefficient of friction of 0.2. And how far below the center of mass of the lamp can the person push so that the lamp slides at constant velocity without tipping? Okay, so our unknowns are actually a force and a distance, and that's not unusual to have not just solving for forces, but actually solving for one of the moment arms. So what we don't know is we don't know FP and we don't know X. Okay, those are our unknowns. So let's choose our pivot point. So we're going to choose a natural choice for a problem like this. We're going to choose the front corner of the base. All right, so this is our pivot. That is the choice that I would recommend because it is the only location where two forces act. So by choosing that as our pivot, we are making two of our forces have zero torque, which makes our torque equation more effective for calculating a value immediately without doing a lot of substitution in algebra. Also, physically, it makes sense. Not that it matters where you choose your pivot point in terms of where things would actually pivot, but the reason that the friction force and the normal force are located at that front point, as opposed to say being located like right below the base, for example, is because if the lamp was to start to tip, it would tip there. And since we're pushing with a pushing force that's just big enough so that we're at the threshold of tipping, that means that the actual only contact point would be the front. So essentially, the lamp has already started the tip, but negligibly so that's why we see the normal force actually only acting at the front edge rather than the middle, where you might think, because normally you would absolutely put the normal force in the front. But for any tipping problem, whether it's tipping backwards or forwards, the normal force will always be at the point where it would tip. So if the lamp was to tip backwards, the normal force would be in the back. But that's not the concern here. We're concerned with the lamp tipping forwards. Okay, so it's a good thing to remember, and it applies to this category of problems of tipping boxes or tipping lamps and the like. And generally, these types of problems are dynamic equilibrium problems. They usually involve some constant velocity. But again, it's not so important for the problem, just for the kind of conceptual setup, because mathematically, dynamic equilibrium works out the same as static equilibrium, right? With that non-zero velocity in the dynamic case. All right, so let's get into the problem. So let's write out our equations. All right, so our 1, 2, and 3 equations. All right, so F net x. Okay, because we've chosen our pivot point, so we're on to this step here. So F net x is going to have the pushing force in the positive x direction, it's going to have the friction force in the negative x direction, and it's going to equal 0. All right. F net y is going to have the normal force in the positive y direction minus mg, and it's also going to equal 0. Torques about the pivot, all right, are going to be, well, these two have 0 length moment arms, so they create 0 torque. So let's think about the torque created by the positive torque, the first torque that's positive. So there's only 2 torques, right? 2 non-zero torques. One of them is positive, one of them is negative. So gravity is going to create a positive torque because gravity would want to twist the lamp in the counterclockwise direction, right? If we were allowed to let it pivot, if we got rid of the floor but kept it connected right there, we'd imagine the whole lamp would be spinning this way. All right, so that's a positive or counterclockwise rotation. So that means we're going to have this torque is mg and then times 12 centimeters, which I'll write as 0.2 meters, 0.12 meters. Okay, and again it's positive, and the angle is going to be is 90 degrees, right? Because if you look at the angle between the moment arm, right? We have we have some distance here, so we could take that total distance, but we only care about this component of the distance, right? So if I look at this as r, I only care about r perpendicular, that being perpendicular to the force. That's the only component that is actually going to contribute. So essentially, if I had done sine theta and this had been r instead of 0.12, then when I did r sine theta, well, that's exactly equal to 0.12. So r sine theta equals r perpendicular, and the angle that we have is this angle right here. That would be our theta. Okay. All right. So I'll just leave that, and I'll put this value back. I can leave the chicken scratch on the figure. Okay, and then we have our negative torque, which is then going to be minus the pushing force, one of our unknowns, times our other unknown, times x. Okay, and again, the angle is going to be 90 degrees because this force is perpendicular to this distance. Right, so if you just look right here. Right, that creates our perpendicularity. All right, so then let's try to solve for, oh, well, of course, we need to write that these torques are equal to 0. Okay, so now we want to solve for Fp and x. Okay, so a lot of times the torque equation is ready to solve for one of our unknowns. In this case, we have 2 unknowns in the torque equation, so we can't solve for it. And we're only asked to solve for x, but we have to find p in order to solve for x. Well, we can look here and see that the pushing force has to be equal to the friction force. Okay, so let's then move on with our calculations and solving the problem. So we have that the pushing force is equal to the friction force, and the friction force is equal to mu k Fn, and Fn, we can see from sum of forces in y, is just equal to mg, which is going to be the case for flat ground. So it's not, rather than a component of mg. So it's just going to be mu k mg. Okay? So then we can go ahead and substitute that into our torque equation. All right? So then we're going to get that we have mg times 0.12 meters minus mu k mg times x equals 0. All right? Go up here. And that means that x is going to be, and let's cancel out our m and our g. All right. X is going to be 0.12 meters divided by mu k. All right, so let's do that over here. So 0.12 divided by our friction coefficient, which was 0.2, as you can see if you look up here. Our friction coefficient is 0.2. All right. So divided by 0.2. So we get a height of 60 centimeters. All right. Excellent. All right. So let's do. Okay. So equals 0.60 meters. Okay. and see how far below. Okay, so I solved for x, our center of mass. Height of center of mass of x equals is 0.75. Now I realize that there's an unfortunate kind of confusion here with the variables, because here I say the center of mass is at x equals 0.75. Really, I should have called it any other variable other than x. So we can just replace it here as h. And it's not even shown in the figure, but if I was to show it, it would be this right here, because clearly it's not x because the center of mass is higher, right? So that's h. That's our 0.75. All right, so that's definitely a badly labeled variable there, because x is labeled in the figure and it's not the x that's mentioned in the body of the text. But the problem is actually asking for the difference between the two. So then we can finally find, we could call this variable here d. All right, and so that's what we're asking for. We want to know how far below the center of mass. Okay, well then our final answer is going to be d equals h minus x, which is going to be 0.75 minus 0.6 meters, which is going to be 0.15 meters. Okay, so the idea is if the person was to push any lower, the lamp would tip over because there'd be too much torque. And the person's always going to push with a force that's equal to the friction force, because otherwise the lamp would accelerate. And so that's fixed. We know the pushing force. We could have solved for it. We weren't asked for it. But importantly, if we don't want the lamp to tip, in addition to not wanting it to accelerate, then we need to push exactly 0.15 meters below. Okay? All right. So that is an example of dynamic equilibrium. Thank you.